Hello and welcome to CERN. We are at point 1 of the Large Hadron Collider inside the ATLAS experiment cavern. So the ATLAS experiment is the largest experiment here at CERN, and it's also made up of a collaboration of some 5,000 people, all working together to explore some of the mysteries of the universe through studying of particle physics. Now, we're actually here to introduce you to a new upgrade of the ATLAS experiment, that is the new Small Wheel, and I'm thrilled to have with me Professor Theo Alexopoulos. He's a professor with the National Technical University of Athens and has been a long-time member of the ATLAS collaboration. Since 2001, you've been working on the muon systems, and he was actually one of the key people responsible for designing and constructing this new detector you see in front of us. So thank you so much for joining us.
Thank you. Thank you, Katarina.
So this new Small Wheel detector is a key upgrade of ATLAS. Can you tell us more about why we need to upgrade the experiment?
Yes. So the way that we took is to upgrade the ATLAS detector, because the LHC has been also upgraded, and it will be upgraded more. We have two phases of upgrades, and so we had to build a new detector to replace the old small wheel that was sitting in the same area that you see right now, in order to cope with the higher rates of particle getting there, and also to make sure that we can select the good interactions by using a trigger system, electronic system, using the detectors, and get only the good particles, the good interactions, in order to discover more things.
Yeah, that's one of the things people don't know about the LHC, is there's a lot of collisions. We can't study all of them. So triggering, selecting the best collisions is a key part of what physicists do. So maybe we should see some of the footage of constructing this incredible detector, which was actually not built here in the cavern, it was built above ground.
Correct. So the way that we decided to go is that the modules, the detector modules, they were built all over the world in actually 11 countries. So they came here. The same the electronics, they were built in 6 countries. They came here, and then we had to put everything together. So that means you have, as you see in the footage now, you see the construction, the commissioning of these detectors. So each, imagine the wheels like a pizza, and then you have the slices, and you have 16 slices there, as you see. Right now, the last slice getting into place. This slice, the one that you see there, we call it sector. Mm-hmm. It covers more than 85,000 channels. So you can imagine how complicated it is, just only one sector. And because the total number of electronic channels we're talking is 2.5 million channels.
On a single wheel.
In both wheels, sorry. Both wheels. Yes,
okay.
2.5 million channels. So we had to build this on a surface laboratory in the main campus of CERN, and then move this to point 1 and install it. And you see, right now we are very excited to see this object, and all the credit goes to the collaborators all over the world that they built this equipment. Right now you see only the one side. As we speak, we are building the other side, so in that lab, as you see in the footage, in this old footage. So there is another wheel that is being built right now in the lab, and it's being commissioned there.
So when will that wheel be installed in the ATLAS experiment?
So that, yes, the next wheel, it will be installed in October, middle of October of this year. So we're hoping to finish everything on time and bring this in place in middle of October. So that's one other thing that we should mention it, is that this object is a 10 meter in diameter. So it's a big object. It looks small.
It looks small
right now, but
only in here though.
Yes, with respect to the big wheel that you see on your left there, with the TGCs, with the thin gap chambers. Also to mention that what technologies we used to build this wheel, we followed a conservative way. That means we used the TGCs, the thin gap chamber, gaseous detectors, with an upgraded version of it actually. and so we call it STGC, the small strip thin gap chambers. That's what I call the conservative approach. And then on the top of it, we used the micro pattern detector technology, and we used the resistive micromegas to build, to make these objects now, as you see it, in place.
Going back to your pizza metaphor, we have two flavors of technology on this pizza.
That's correct.
Micromegas and the STGCs. And one is a more exotic of these.
Exactly. It's exotic in the sense that originally we started with the R&D with a small size, like 10 by 10 centimeter square, and then we went wild and we built 2 square meter modules. You can imagine this leap is not an easy leap to do it, but we spent a lot of time. We spent, the project was approved in 2012, and so about, as you see, many
almost
years.
A decade.
Almost a decade
to this
ago,
day.
and now we went through many ways to resolve many problems in order to achieve, to build these wheels.
So not only constructing it was a major accomplishment, just transporting it here from Building 191, the site on CERN, was quite a feat. So if we can see some footage of the movement from Building 191, it was, I mean, Building 191 is about 2 kilometers away
Exactly,
from the
about 2 kilometers away. So it took about 2.5 hours to bring it here. And what you see in your footage, you see the movement. The movement was with the specialized tracks, because the track has to be horizontal all the time, because you imagine this 10 meters diameter object plus the platform of the tracks that created, the center of gravity is really way up, so you have to be really careful. That's why it took so long to move it from Building 191 of the main campus to Point 1.
And once it got here, I mean, there was still a lot of work to be done. We had to carefully unwrap it, make sure that no moisture from the transport build up on the inside. And if anyone watched the live we did on Instagram on the Atlas channel that day, they will know that it was pouring rain the day that this wheel came. And yet here it sits in the Atlas cavern, dry and safe, because it was so well transported.
That's correct. It was very well covered, and was decided to move that day. And so it was the 6th of
last week.
Yes, of this month. And but it was well covered, so no problem, no accidents. Everything arrived on time and alive.
And alive. Well, it's many years of people's work, and so of course people are very careful in transporting it. And then of course it got above ground, but then we needed to get it underneath. So we have some wonderful footage of the lowering of the new small wheel underground, and because it's one thing to get it here, the 2 kilometers, but then we have to bring it down almost 100 meters down the shaft of the experiment.
That's correct. It took about 2 hours to bring it down to its parking position, as we call it. And then right now what you see the object in the position that is close to its standard opening position, we call it, because then you can imagine we have to connect everything, the services, because those are gaseous detectors, so they need the gas. Then we need to connect the water, because we cool all the electronics with water, to connect all the fibers in order to get all the signals out of the detector, and to connect all the possible cables that you can see around this object in this disk. So after this connection is done, then this object can move to its final position or running position to be ready to accept particles, let's say, and identify particles.
No, I mean, it's a very complex detector, and a lot of times we only talk about the detecting part, but there's of course all of the connections that go into making sure we get the correct data from the detectors we have in place, and those are just as important, because
absolutely, it's very important, yes. And you can imagine all the complication. So you have to validate all the cables, you have to validate all your electronics. So what we do this validation at some integration labs, we call them, because we have to put together all the modules of the detectors, then the electronics, the cabling, the services, and then you have to make sure you understand the way that it works, each of these slice or sector, as we call it.
So, I mean, 10 years of work went into making this, lots of collaborators,
Yes.
many countries involved, and the day of the lowering was quite emotional, wouldn't you say?
Absolutely, absolutely. You know, it's one of these things that in your dreams, sometimes you think that probably it's not going to happen. You know, you have nightmares, but these days, you know, since last Monday that it got into the pit, it got into the cavern, it was very exciting, of course, for everybody. It will be more excitement in October when we will move the next wheel on the other side of the cavern.
So we'll be able to witness this lowering all over again. But my understanding is that the next time we lower it down, it might be a little more complicated because the shaft is a slightly different size. Is that right?
Yes, but imagine there is a lot of experience right now, bringing this here and put it down, and I hope it's not going to be a problem. And also the complication of connecting all the cables and make sure that everything is working properly, since we are getting now experience in these next 2 weeks that we'll do all these connections, and further into the future before LHC, before we hand this to the LHC, and this is going to happen eventually at the end of February, beginning of March. Let's say
Next year.
next
So,
year.
if you're just joining us now, welcome to the Atlas experiment. We are here in front of the new small wheel detector. It's a brand new addition to the Atlas experiment, and we're actually taking questions live from you in the YouTube chat on Facebook. So please do send them in. We have our first one, which is from Alsam. So he asks, what is the expected data for starting from taking data for run 3? So how much data are we expecting during run 3?
Well, I mean, it's imagine that at the beginning is going to be the test runs, right? So what we expect is at the end, just to give you an idea, in the middle of, in the center, where it's the more active part of the particles that are getting there, we expect about 25 kilohertz per square centimeter. So that will be, to give you an idea, the rates that we expect at the high luminosity LHC.
So that will be high luminosity, but for our next run, what are we expecting?
This is going to be lower, so it's going to be less than 10 kilohertz per square centimeter.
Which gives you an idea why we need an upgrade so much. So the next question is from James Moore on YouTube, and he asks, how long will the connections and validation process take?
Okay, that's a very good question. You know, it's the first time we are doing it, and so we think that it's going to take 2 weeks, initially 2 weeks, but the validation, of course, is going to be now for the next months until the LHC. We hand this to the LHC. That means sometime in February. So we can work on and off around there to validate everything.
So another question from Facebook: what was the most challenging part of this upgrade? Maybe personally, you could answer that.
Well, it's there were many challenging. First, as I said, we decided to go wild with a new technology, from a small object to really large object. So this is not easy, and of course we're not the first ones that we see these kind of things. So, but with dedicated people, you can achieve this. So, technology, the chosen technology, the micromegas and the small and the STGCs. Also, it was very challenging to build this big object. Then electronics, the rates, they were really high, so you had to build new specific ASICs. And
what's
chips.
an ASIC?
Yeah, the chips you have in your computer. Let's say you see something there. Let's call them chips. And so this was challenging. And then the mechanical part also. It's to bring everything there, because everything is 90. I don't know if we mentioned this. The weight is 94 tons, and to hold this vertically and with this accuracy that we need there, it's remarkable. So there are many challenges. It's not only one challenge.
Lowering it down alone
Lowering,
was
exactly.
a challenge.
Moving
in and
it
of itself.
also with the trucks, with these specialized trucks into the place, it's a challenging problem as well.
Okay, so next question. How many people are involved in hooking up the detector?
Okay.
That is from GS on YouTube.
Okay, right now you mean hooking up now?
Yeah, so, well, I
Let's
mean,
see.
right now they've finished
Okay.
their day, but
Yeah, okay.
once
yes.
they come back to work,
Yeah, okay. There is a team. There. As I said, I mean, just let's go back a bit. So there are people at the integration sites. They put everything together, and then we have 2 integration sites, one per technology. Then we have the commissioning site where you bring everything and you hook them and you put everything on the wheel, and then you have people, the same people also, and some more colleagues are coming to help here. So we are talking about overall about 100, more than 100 people working on these things. So right now in the cavern there are about overall about 20 people that they are involved in this, and these are same people at the integration sites coming here, helping and so on, because you need experts.
you need to know your detector. You're not going to
Exactly.
trust it to just anybody.
Exactly.
It's a lot of work. So another question is a little bit more about discovery. This one's from you too. So what sort of objects do we expect to discover with Atlas? I guess what sort of physics are we looking for with
Okay,
Atlas?
well, this is going to the unknown, of course. The first thing is we have to study, all these upgrades are done in order to study the Higgs particle, the properties of the Higgs particle, how it couples with other particles, and learn more about the Higgs. The other thing is to learn something beyond the standard model physics. So we need a lot of statistics in order to see details and to understand if there is something beyond the standard model. So there
New
are
physics.
Sorry?
There's a lot of new physics out there.
absolutely
The standard model
Yes,
is what describes, all of the matter we were made of, and so much of our known universe. But there's still so much left to explore.
exactly.
And hopefully, with Atlas and the next coming data sets, will be it's the perfect
Yes.
time for that.
Let's hope.
So another question from Facebook: do the other LHC experiments are they also doing upgrades at the moment?
They are doing, yes, they are doing, but I think this is the largest one right now with respect to the number of channels and so on. But as I said at the beginning, there is another phase. So there are colleagues in our experiment in Atlas, but also in other experiments. They are working for upgrades in phase 2. That is going to be happening 2025, 2026. So there are upgrades for the inner detector with the silicon that is also very complicated objects, but those they will be happening
Coming later.
phase, yes.
So I mean, one of the things that people might not know about the LHC is that it actually operates in between periods of shutdown, and during those shutdown periods, upgrade work takes place not just on the experiments but also in the accelerator. And we've got to plan ahead for many shutdowns to come. So we're currently in long shutdown 2, and we're already talking about long shutdown 4.
Yeah, exactly.
It's a massive collaboration, a massive project, and we've got to look far in advance. So another question, how many cables did you connect to the new small wheel?
Myself,
Well, I'm going to take this as a personal question. How many did you connect to the new small wheel?
well, actually I connect many cables, but it's not myself. You know, we have dedicated teams, we have technicians, we have students that they help us on this. So myself, I don't know the number,
Quite a
but
few, quite
let's
a
say
few.
quite a few, okay. But all the credit goes to all the people. I mean, it's a very collaborative work. That's the message. It's not only one person. There are many persons that they have contributed, and graduate students, which is our driving force, dedicated graduate students working 24 hours per day. I'm not joking sometimes, in order to achieve what you are seeing there.
Very
And-
dedicated. And part of the thing is we need to make sure we stay on schedule because the accelerator cannot wait
Correct.
for these things to get done. So another question, how many electronic chips are custom made and which ones can be bought off of the shelf? That's a nice. That's a
Yes.
nice. That's
Okay,
a nice question.
there are different types of chips, and so we customized about I would say five types of ASICs, and the rest, of course, to build a circuit, you need also to use resistors, capacitors, and all of the other little connectors and so on. So those they came from industry, of course. You don't have, but the ones that we customized for our process, there were about five types of different chips.
It's a bit of a mix. It's a bit of
Yes,
a mix.
it's absolutely has to do.
So we had one question a little earlier, which were what were the next steps for the detector upgrades?
The next steps, or you mean a new
Maybe
small?
after the new small wheel.
The new small.
Phase 2.
The phase 2 is the inner detector. So it's and also for the muon systems will be the inner layers of the muons. They will be replaced with a smaller diameter tubes and an RPC system, triggering system. So it will be
Maybe
a
you
major.
could point out where we're talking about.
Yes, well, it's hard to see. Imagine this as a barrel. So the barrel has three layers. So you have the inner layer, the middle layer, and the outer layer. You can see the outer layer.
You can see these outer layers here.
Yes,
These are
those
the
big
silver.
ones. The inner one, it's smaller, of course, in size, and those they will be upgraded and will have. Actually, as we speak, a small upgrade has been done with respect to this project of phase 2 in phase 1. So we call
starting
BIS.
early.
Yes, started already. They have installed it, and they have done a very good job there to install this small tube with the RPC with the trigger detectors in place.
So these are all muon systems.
Exactly, this is the muon, and then will be the inner detector, that is the silicon detector.
Okay.
That is going to be phase 2.
I think the muon system is maybe if you ever visited Atlas or you ever get a chance to visit Atlas, you will doubtless see the muon spectrometer because it makes up these giant wheels in front of us.
Correct.
So we are actually going to
Yes,
we are
okay.
actually going to be going over to Instagram after this. So we're going to be doing another Instagram live, and Professor Theo, you're going to be answering some more questions. So if you have any more, we suggest you head over to Instagram to ask them there. So thank you very much, and thank you very much. And we're going to be heading
That's
out.
all. Okay.
Work day is over. So thanks for joining us, and thank you, Theo.
Thank you. Thank you.